Welcome to the next lecture. As I mentioned in the beginning of molecular thermodynamics lecture is that this particular subject can explain macroscopic observations because of averaging. It is all in the average as it is mentioned. We will explain to you in a moment that thermodynamic observables such as energy, pressure, volume are averages weighted by the probability. And you know by probability what we mean is that the probability is associated with a particular type of systems. We talked about three different kinds of probabilities. One associated with the classical systems, classical particles which gives rise to Boltzmann distribution. We also talked about bosons and fermions giving rise to Bose-Einstein statistics and Fermi-Dirac statistics. So, these different statistics gives us probabilities of particles occupying a certain energy levels, and once we have the probabilities, then we can use these probabilities as weights in the average calculations. For example, I mentioned to you before that if I let us say calculate the average age of either Pune students, then all that I can do that in two different ways. I can sum up the age of all students and divide by the number of all students, or I can associate weights to each batch of students, assuming that the first year batch has first year batch has all age of 18 and I know their number, then I can use that information to write like this, that 18 is the age multiplied by the number of students plus let us say second year students maybe 19. So, 19 multiplied by the number of students from the second year, and then 20 multiplied by the number of students of third year, and then I will divide by the to all the weights, that means number of students from each year. So, this is called weighted averaging, and in statistical thermodynamics we do weighted averaging in order to get the average property. For example, when I talk about the average energy, it is EI Pi, Pi is the weights and EI is the energy. Now, you know that Pi is basically Boltzmann distribution. For example, we know that Pi is e to the power minus beta EI or e to the power minus EI by kBt, beta is 1 by kBt. Now, if a particular state has lower energy, then this quantity will be if it is lower energy, it will be small. If it is lower energy, let us say it is more negative. Lower energy means let us say EI becomes more negative, then this quantity will be larger. If it is higher, a positive quantity, it will be smaller, and therefore, Pi for a low energy state will be higher, and therefore, it will contribute more to the system, which means that when we calculate the average property, the average will be governed by the systems which are of lower energy. I will give you an example. Let us say we talk about protein folding. You know the folded state is more stable, therefore, it has lower energy, and unfolded state will be less stable, and therefore, it will have higher energy. Now, when you calculate the average property of the system, it will be governed by the folded state, not the unfolded state. However, there is a catch to that. You will see that folded states, there is only one possible ways of getting perfect folded state, that which you call as native state. However, there are many other ways of getting an unfolded state. So, there although each term will contribute small amount, however, there will be more number of them. So, and that is essentially what we are talking about as an entropy contribution. That means, there are more possibilities for unfolded state to be present, therefore, the entropy of the unfolded state will be more, and there is less possibilities for the folded state to be present. So, entropy will be less. However, energetically folded state will be more stable than the unfolded state, and this balance will lead to a smaller difference between the folded state and unfolded state. So, idea behind that is that all that we calculate, all that we observe, they are nothing but the average properties associated with the weights, and weights here is associated with the energy of the particular system. Similarly, we can talk about pressure and volume as well, and this reminds us of what we have observed in the expectation value of the property in quantum chemistry. So, you remember in quantum chemistry the expectation value, which is nothing but the average value of any property A is given by this particular equation psi star A psi d d tau, if I want to be more general. And then this A is an operator, but once it operates on the psi, let us say we get some value, it need not be an eigenvalue, let us say that we get as A. So, then this one immediately will give us psi star psi A d tau. Now, psi star psi you know as a probability density. So, it is almost like our Pi, and A is something like the property which is our EI, and then this corresponds to the same as the above equation. So, that is why, and you know, since this one the statistical thermodynamics came before quantum mechanics. So, remember it started from 1872 by Boltzmann, and quantum mechanics came around 1925. So, since the statistical thermodynamics came before, this probability is used to be called the new probability. The idea behind both of them essentially is the same, that we only observe what is the average value. So, in order to give you an example, we are going to talk about particle in a box system. So, this derivation I will show you in a moment, but before that let us just do the derivations ourselves. So, let us do the average energy calculation for a particle in a box system. So, average energy or energy of a particle in a box system E n is given by n square h square by 8 m L square, where n is 1, 2, 3 up to infinity. And when you draw that, we have seen that how we actually normally represent it like that. So, this is n equal to 1, n equal to 2, n equal to 3 and things like that. Now, the partition function of the system Q is given by, as you know, I e to the power minus E I by k B T. Here I denotes the energy level. Since we are denoting energy levels by n, we can write that as e to the power minus E n by k B T, where n goes from 1 to infinity. So, if you specify that, it will be minus n square h square by 8 m L square k B T. Now, this is a sum, and that sum is a discrete sum. It goes discretely from 1 to and different levels. However, sometimes it is helpful to convert the sum to an integration. So, for example, if I summing n equal to 1 to infinity, and when there are so many values present, we can imagine that the differences are actually smaller, and then we are integrating over all possibilities. Although we are in that we are taking all possible values of n, we can write that as an integration of d n that goes from all the way from 0 to infinity. We are adding more values in between, but we are assuming that since we are doing like infinite number of points, that is why these differences will not matter so much. So, it is called discrete to continuous approximation. Similarly, so then in that case we can write the sum which is there on the left hand side as n equal to 1 to infinity e to the power minus n square h square by 8 m L square as integration of e to the power minus n square h square 8 m L square d n going from n equal to 0 to infinity. Now, in that we are talking about a fixed value of L, which means that this quantity which is there on the right hand side, it resembles an integration going from 0 to infinity e to the power minus a x square dx. This type of integration is difficult to solve, at least in the 12th standard level. However, one can use some formula for standard integration in order to do this type of integration. This is called Gaussian integral. And there is standard value available for that. For example, the standard value for 0 to infinity e to the power minus a x square dx is half root over pi by a. For minus infinity to plus infinity, it is just root over pi by a, and for 0 to infinity, it is half root over pi by a. So, we are taking that n equal to 0 because then it helps us in doing the integration, and since we are taking so many integers anyway, then adding one more is not going to matter so much, because n equal to 0 is going to add 0 value to that. So, when you are doing the integration, we are summing up all values. So, there we add the 0th value, 0 value also. That is not going to change the result, because we are adding a 0 value. If you put n equal to 0, you are going to get 0 energy, and that is not going to change the partition function at all, which means that this sum I can also write as n equal to 0 to infinity e to the power minus n square h square 8 m l square, because in a sum I can always add an extra 0, meaning of course, here of course I am adding not 0, I am adding value 1, I am adding an 1 value, but that is again not going to change the sum which is there for infinite number of steps. Now, once we do that, then what is our a here? Now, if I compare this equation with this equation, once I compare these two, I see that my x is like n and my a is h square by 8 m l square. So, therefore, my result for this particular integration will be half root over pi by root over a, which is root over of h square by 8 m l square. Okay, I forgot to mention one thing, there is a kBt also down here. So, here it will be kBt as well. So, it is E square by kBt. So, I will just correct that. Yes, as you can see, there is a kBt here. So, there is a kBt there as well, and there is a kBt there as well. It is E by kBt, right. So, is going to write that. So, in that case our this thing has kBt here as well, and that is what we get. Now, which means that I get half, this term will go in the numerator, it will become 8 m l square kBt by pi, no, pi will be on the numerator itself, it will be h square. Anything else I am missing? 8 m l square kBt pi, and the whole root will come. Now, put the 2 inside, what I am going to get is 8 m l square kBt pi by 4 h square. I put 2 inside and it gives me 2. So, I get 2 pi m kBt by h square to the power half into L. So, that is the partition function that I got for particle in a one dimensional box, and you know what partition function is, it is just the sum of the exponential of the energy values. So, this partition function I got as Q, and now we have to see that how we are going to get the average energy. Now, in order to calculate the average energy E, we have to write as EI Pi, and EI Pi is nothing but EI e to the power minus EI by kBt divided by sum over e to the power minus EI by kBt. So, in order to obtain this particular relation, we need to use a trick. I will tell you what the trick is. So, if my q is this, then if I take del ln q by del t, what I am going to get? Let us see. If I do that, then I am going to get del ln q by del t is 1 by q del q by del t. So, q is this one. So, I am going to get 1 by q into del q by del t. Now, let us differentiate this quantity, and if I do that, I am going to get e to the power minus E I, and there is a sum there, sum over I e to the power minus E I by k b t, and then I have to take the differentiation of E I by k b t with respect to t. So, I will get E I by k b, and then 1 by t is there. So, I will get minus 1 by t square. So, let us simplify that. I get E I e to the power minus E I by k b t. Outside I will get minus 1 by k b t square divided by e to the power minus E I by k b t. So, once that happens, so what I am doing now, del ln q by del t. So, minus 1 by k b t square, on the right hand side, all this particular quantity, this quantity will resemble, as you can see, exactly E I P I, okay, which means my del ln q by del t is nothing but 1 by k b t square and average energy. So, average energy therefore, is minus k b t square del ln q by del t. Why I do that? Because I have my q already written. What was the q? I will show you. My q is this quantity. This is my q, 2 pi m k b t by h square to the power half into L. Okay. So, that means I have to do del ln. So, now if I want to get the average value, I have to do del ln q by del t, which is del ln q by del t of this particular quantity. So, let us do that. So, this quantity is del ln q by del t into minus k b t square I have to do. So, let us do that. Minus k b t square, first I will write it, multiplied by, I will do the differentiation of q. So, del ln q by del t is 1 by q del q by del t, 1 by q into del q by del t, which means I have to take the differentiation of this guy. Now, in that 2 pi m k b h square, they are all and L, they are all constant, half and L, this is all constant. So, I have to basically do t to the power half derivation. So, t to the power half is half t to the power minus half. That is now, our thing is now almost done. Now, let us see what it gives us, minus k b t square into, now 1 by q will be h square divided by 2 pi m k b t to the power half, and there will be an L there, 1 by L, multiplied by 2 pi m k b by h square to the power half into L is there, and there is a half here which I am writing here, and t to the power minus half which I am writing here. Now, let us see what are the things that are going to cancel. h square going to cancel, 2 pi m going to cancel, kb also going to cancel, L is going to cancel, giving us minus kBT square by 2, and then I have 1 by t to the power half, and I have here also 1 by t to the power half. Okay. I am missing some quantity, let me see. So, minus kBT square is fine, 1 by q del q by del t. Now, when I do del q by del t, I have this constant quantity 2 pi m kb. No, so this there also there is a t there. No, not t. So, 2 pi m kb by h square to the power half, L is there, t to the power half is there. So, t to the power half is half into t to the power minus half, that is also there. So, now I have minus kBT square by 2, this is fine, but I am getting minus, minus, there is a minus missing somewhere.
Sir, in differentiation, sir, in above, where you have done the del n q by del t, that will be the plus kBT.
Correct. So, let me see that. So, del n q by del t, let us review that, 1 by q del q by del t. So, 1 by q is given in the first step, 1 by q, and then I have to differentiate del q by del t. So, e to the power minus e by kBT, and then I have my ei by kb, and then I have a minus there, and there is minus already is there, and then minus becomes plus. So, I have plus, and I have plus here, I have plus here, then I have plus here, I have a plus here, I have a plus here, I have a plus here, and that is giving us kBT square by half into 1 by t is half kBT, and that is the average energy of particle in a box, in one dimensional box. So, if I now take it to the 3 dimensional box, you can see that all the dimensions are independent. Therefore, the average energy for a 3D box will become half kBT plus half kBT plus half kBT is equal to 3 by 2 kBT. Now, you know that from the equipartition theorem that for every dimension there is half kBT energy is there for translation, and therefore, for a 3 dimensional system the average energy classically is also 3 by 2 kBT. So, we can see that for non-interacting systems like particle in a box, which does not interact with anything and does not have any, so it has only the translation energy, the average energy is also giving us the same value. If you use the classical description, classical kinetic energy like p square by 2 m, and that also average you are going to get as 3 by 2 kBT. So, that is one of the example that how the average energy is coming to be 3 by 2 kBT using the formula of molecular thermodynamics. So, all that we have done is that we have taken all possible energy values like n square h square by 8 m l square and weighted them by their corresponding Boltzmann probability, which is e to the power minus E I by kBT, and then we took the average of that, and once we do that we are getting to see that it is nothing but 3 by 2 kBT. So, like that you can apply this for many different possible systems, and then we are going to get the desired observable values from the what we see in the classical thermodynamics. So, that is where the connection between molecular thermodynamics and classical thermodynamics takes place. So, for example, when we do simulations, computer simulations of particles, there also we actually move atoms and molecules every time step. So, we have their positions and coordinates and then velocities, and after that, after doing the simulations, after generating so many different microstates from the simulation, we calculate the average property like energies, free energies and all that, and that reproduce the experimentally observable quantities. For example, binding energy of 2 proteins. We can do that from simulations just because we know that by following the formula of statistical thermodynamics, once you calculate the average property, it is going to correspond to the macroscopically experimentally observable quantity. Without that, molecular thermodynamics would not have worked. So, that is where the connection lies. You can see the derivation here also, and you can see that, yes, here also you can see that this is plus kBT square, and I have done directly for the 3-dimensional box in this particular case. So, now just brief review entropy in a nutshell is that for a spontaneous process, system increases towards a more probable state. That was the second law of thermodynamics from the statistical point of view. W of the most probable state is the highest. So, when you calculate W from many different distributions, but the W corresponding to the most probable distribution will have the highest value, and that is enough, that is the only one that you have to take. We have seen that energy is not conserved, energy is conserved, but the distribution of energy is not conserved, because we can either accumulate all the energy in one place, or we can, that is called a peak distribution, or we can make it flatter, that is flat distribution. And because the distribution is not constant, we know that entropy also will not be constant, because entropy will go by the probabilities of distributing these energies. Okay, as I said, entropy is nothing but the distribution of energy.